Still going? Okay. All right. So there are certain elements that have Roman numerals. And let me kind of give you a historical perspective. So it used to be when you named iron, for example. So the Fe for iron comes from the word ferrous, it's a Latin word. So iron has two most likely oxidation states. It can be Fe2 plus or it can be Fe3 plus. So how they used to name it in the old style, because sometimes you'll see bottles labeled this way in the storeroom. They used to name it ferric, and I'll never ask you this on the test. This is just a historical perspective. Or ferrous. Okay? So here was the nomenclature. And you would always hear people in the lab room saying this, and if you didn't know what it meant, you would think that people were crazy. They'd always go, ic is more, us is less. Ic is more, us is less. So that was referring to the oxidation states. So ic is more, so if you had like ferric phosphate, that would meaning that you have Fe3 plus. If you have ferrous phosphate, then that's Fe2 plus. So if you were in the lab and trying to find this bottle, and you wanted, Fe3 with the phosphate, you'd find ferric. If you wanted Fe2 plus with the phosphate, you'd find ferrous. So you'd see people in the lab, ic is more, us is less. And it's true, whether it was, anything that had more than one possible oxidation state. So they said, okay, this sounds really just stupid. Why don't we use Roman numerals? And so remember, what the Roman numeral is going to indicate isn't the number of atoms, it's that oxidation state. And you only have to put Roman numerals if there's possibly more than one oxidation state. So what this is saying is that you have Fe3 plus, you have phosphate PO4 3 minus, it's 1-to-1 ratio, so it's just FePO4. So that's just FePO4, boom, there you go. Don't make it complicated. Don't transfer the 3's because it'd be like redundant. Don't have like 3 Fe's and then 3 PO4's. Don't do anything like that. So on number 2, when you're writing the names, with that one you should have a total of 2 of those names that have Roman numerals. Okay? And so if you're not sure if they have Roman numerals, look on that sheet of ions that I gave you, okay? And if you see any of those that have like more than one oxidation state, that means that you have to put the Roman numeral with it. So on number 2, you should have 2 of them that have Roman numerals, okay? Just 2, that's it. On number 3, because you're finding the percent composition based upon atomic mass, this isn't based upon numbers. So you have like sodium hydrogen carbonate, NH3CO3. So here's your process. You need to find the molar mass of sodium, which is like 23. Now, when you're doing this level of AP chemistry, when you look at those relative atomic mass numbers, and let's talk about what the relative atomic mass means, because that's going to play out large in just a second. So, a little historical perspective on relative atomic mass and how it came to be. If you go back to how they originally laid out the periodic table, they didn't know anything about S sublevels, P sublevels, D sublevels. They didn't even know the nucleus existed. Okay, at the time, they thought the atom, and that comes from the Greek word atomist. They thought the atom was the smallest possible particle that you could have. Okay, so they had no concept of protons, electrons, neutrons. Even if you look at like chemistry books that even from like 100 years ago, if you look in the index books of chemistry books from 100 years ago, from 1920, you will find no mention of electrons, protons, and neutrons. We did not know that those subparticles existed. Okay? J.J. Thomson was the first one to find the electron, and then they figured out, and then Ernest Rutherford did the gold foil experiment, and he found the protons and the nucleus. Okay? So it's a relatively new discovery that we know about these subatomic particles of electrons, protons, and neutrons. So how Mendeleev initially laid out the periodic table is that he arranged them based upon relative atomic mass and also their chemical properties. So how they figured out relative atomic mass, and this is like in the 1800s, okay? This is well before you had any kind of computers or any kind of high-tech ability to measure mass. So basically they said, okay, we're going to take a very common element, and we're going to establish that as like a relative mass. Okay, so they picked carbon-12. The reason they picked carbon-12 is because it's pretty easy to make a pure substance of carbon. Like if you take green beans and you put them in the oven and you just bake them to death, basically the only thing you're going to have left is this black powdery compound, which is pure carbon. So no matter where you were in your lab situation, it was pretty easy to make a pure sample of carbon. And so that's why they picked that. And the arbitrator, they said, hey, we're going to call that 12. Okay? So just like if you were to, like let's say within the 6 of you, say, we're going, instead of like height, like an actual number, we're going to pick a random person and we're going to call them like a height of 12. Okay, so we're going to pick Kira and we're going to say her height is 12. Okay, we don't know what her actual height is. We're just going to say Kira's height is 12. So if you're like twice as tall as Kira, you're going to have a mass of, or you're going to have a height of 24 because you're twice as tall as Kira is. If you're 1/12 the height of Kira, you're really short, okay, you're going to have a relative height of 1. I don't know what the height is, but we're just going to use Kira as the benchmark, okay? So that's what they did with carbon. They said, okay, hey, we're going to call this carbon-12. We're going to have that as a relative benchmark, and we're going to call that 12. So then they looked like at hydrogen. Okay, hydrogen's the lightest element. Okay, that's really, really light. So they said, okay, that hydrogen atom has a mass of 1/12 that of carbon. Oh, okay, so we're going to let hydrogen be 1. Helium, okay? Helium is like, that has a relative atomic mass of 4. So that means a helium atom is like 1/3 the mass of one carbon atom. Magnesium is 24, so that means a carbon atom has a relative, magnesium is twice as heavy as a carbon atom. So they didn't, this is going to be important, they didn't know the actual numbers. So this is why they call it relative atomic mass and not actual atomic mass, because it was based upon a relative scale. So, and that was cool, and it actually it allowed them to figure out pretty much the arrangement of the periodic table as you know it now, based upon this repeating pattern of relative atomic mass and chemical properties. Now, they didn't know a lot of the elements, because especially the noble gases are extremely difficult to find. Number one, they're gases. Number two, they don't react with anything. So it would be like you go to a party and let's say there's someone that's really, 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 really quiet, doesn't interact with anybody, okay? They just stand over in the corner going, okay? And then later on you say, hey, was this person at the party? You go, no. You probably wouldn't remember them because they don't interact with anything, okay? Now sodium and chlorine, oh my God, oh, they were the life of the party. They were reacting all over the place. It was so embarrassing, okay? So the reactive elements, you're going to remember those. You're going to find those. Ah, did you see them? Like, wow, right? Noble gases, they're in the corner going, okay? It's like, were they there? I don't know, I don't remember seeing them. So the noble gases were extremely difficult to find because they don't react with anything. So, for example, helium, okay? You want to know the origin of the word helium? Where that element came from? It comes from the Greek word helios, which means sun. We didn't even know helium existed until like the early 1900s. And how we first figured out that that element even existed is that we looked at like the photospectrometry of the sun. If y'all remember in Chem 1, did y'all do this where you looked at like, you have like the gas tubes of like neon, argon, whatever, and you drew like a little spectrum? Did you all do that? Know what I'm talking about? Okay? Kira? Okay, so here's the deal. When you look at different elements, nitrogen, especially the gases, nitrogen, oxygen, or whatever, they emit a certain color of light. And if you separate that light into colors, then you get like a band of like blue light or orange light or green light, okay? So you take that light and you separate it out into colors. And each element has its own unique spectrum, okay? And so what they did is they looked at the light was being emitted from the sun. And they saw a spectrum that didn't match with any known gases, like argon, neon, whatever that is. And so that was the first place they saw this particular fingerprint of light. And that's why they call it helium, from the Greek word helios, which means sun. And the reason that you have a helium spectrum in the sun, and this is where a whole bunch of things fit together, is that in the sun works off of a fusion process. You take hydrogen, you slam them together under extremely high pressures and temperatures, you get a helium atom out of it. But in that process, there's a slight loss of mass, which gets converted into energy from Einstein's equation, E equals mc squared. So what they saw is that the reason that they saw this helium spectrum in the sun, because helium is being produced in the sun, and that's what allows it to produce energy. So then they were able to find it for a long time, because helium is such a unique element, because it's lighter than air, that's why you have helium-filled balloons, and it's also not reactive, and so that made it a cool thing. And so there's actually like huge, at the time, we found a huge reserve out in southwest Kansas, and that was actually, they kept it as a national, as like a military national secret, because they didn't want anybody to know about it, because at the time, this was like in World War I, World War II, they needed to use those to fill like the big air balloons that they could use in reconnaissance. So they actually kept the helium field as a secret, because they didn't want any people to know about the fact that we had this large stash. So this is my small little tirade. As you all grow up and you have children, for the love of God, do not buy helium-filled balloons, okay? We only have a certain amount of helium on this earth, and it's diminishing. And we need the helium to run like MRI machines, because liquid helium gets really cold. So here's your choice. You can use your helium to fill up a balloon that's just going to flow away. It's probably filled with mylar, and mylar doesn't decompose, and it's a waste of resources. Or you can have that same helium that you might need for your child to be in an MRI machine to diagnose them with cancer. So those are your choices as parents. You can either have a helium-filled balloon, or you can reserve that helium for medical purposes. Let's err on the side of medical purposes, because little Timmy isn't going to remember the helium-filled balloon anyway. So just, anyway, so, and especially like if you have your graduation parties, tell your folks, no helium-filled balloons. Just say no. Okay, so relative atomic mass. They said, okay, we got this number. But then, and this is going to lead into mole conversions in a roundabout way. They said, okay, hey, you know, if I go to Alan, I'm not going to go to Alan and say, hey, Alan, go into the lab and give me like 5 carbon atoms. Okay, I just need 5. Okay, that's all I need. It's going, well, it's a problem, Mr. Burkett. I don't know how I'm going to get 5 carbon atoms. But what we do is that, and at the time, the metric system was all the rage. So they said, okay, we have these relative atomic masses. How about, instead of like carbon, instead of 12.0 atomic mass units, let's just scratch out the atomic mass units and put grams on the end of it. So this is how a mole came into being. They said, okay, hey, instead of atomic mass units, let's just mark that out, and we're going to start calling these grams. Now, if I say to Alan, I need you to go in and measure out 12 grams of carbon. Oh, hey, that's something we can do, right? Because 12 grams of carbon is about like 12 paper clips, okay? Hey, we can measure out grams. So that's how they defined it as a mole. So literally, all they did is they took the relative atomic mass, marked it out, and started calling it grams. So this is why you define a mole in terms of grams. Now, if you're in physics, they use what's known as a kilomole. So in physics, if I said, hey, if I'm in a physics lab, I said, hey, Alan, go get me a kilomole. So instead of 12 grams, he would measure out 12 kilograms, which is quite a bit more. So in physics, a mole is defined as not grams, but kilograms. In chemistry, it's defined as grams. Okay? So, okay, great idea. So then Avogadro came along, and he actually did his work with gases. He said, look, a mole of anything, and this is his hypothesis, is going to contain the same number of particles, whether it's a mole of hydrogen gas, nitrogen gas, carbon dioxide, whatever it is. Okay? He actually never came up with the number itself. He just proposed the concept. So here's the challenge. the reason Avogadro's number, by the way, what is Avogadro's number? 6.02 times
10 to the 23rd.
times 10 to the 23rd. Okay? So just like a dozen is 12, okay? Avogadro's number is always going to be 6.02 times 10 to the 23rd. Okay? So here's the reason why. It's 6.02 times 10 to the 23rd and not 12 or 14 or whatever. So if I gave Alan the task, I said, Alan, here's your job. I'm going to give you a scale, okay? And I'm going to give you a jar of carbon atoms. And I want you to start counting out individual atoms. These are the magic tweezers, okay? Where you can pull out one carbon atom at a time. So Alan's going to pull out one carbon atom and he's going to put that on the scale. And then he's going to pull out another carbon atom. He's going to keep going and going and going and going and going and going and going. And it's like, Alan, you get to stop when you put enough carbon atoms on there that that scale reads 12 grams. When it reads 12 grams, you can stop. But you have to keep track of how many carbon atoms it takes to get to 12 grams. Okay? So he's going to count and 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 count. And when he gets done, that's going to take him 6.02 times 10 to the 23rd carbon atoms stacked together to get 12 grams. Now, what if carbon atoms were a lot bigger? Okay? What would happen to Avogadro's number? If carbon atoms were more massive, what would that take in terms of the number of carbon atoms to get to 12? Would it take more or less?
Can you like volume-wise?
No, just raw number.
Like mass is bigger?
Yes. So each...
Oh, less.
Yeah. So it would be like, hey, we're going to have ping pong or tennis balls, or we can have bowling balls. This is Hank, by the way. Okay, I usually use him in physics, but we're going to use him here. So let's say that I give Kira the task of measuring out 20 pounds. Okay, what's going to take more particles to get 20 pounds? Tennis balls or bowling balls? What's going to take more to get to 20 pounds? Tennis balls, because each tennis ball has less mass, right? So if carbon atoms were bigger, it wouldn't take as many. But carbon atoms and all atoms are extremely, 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 extremely small. So the reason Avogadro's number is 6.02 times 10 to the 23rd is because it takes that number of particles stacked on a scale to equal the relative atomic mass in grams. Now, if you're in kilomoles, if you're in a physics situation, that Avogadro's number is 6.02 times 10 to the 26th, because it would take another order, 3 orders of magnitude higher to get to 12 kilograms, because 12 kilograms is a lot more massive than 12 grams. So Avogadro's number in the physics class is 6.02 times 10 to the 26th. In the chemistry class, it's 6.02 times 10 to the 23rd. Okay? So there's a historical background on why Avogadro's number is 6.02 times 10 to the 23rd. So when you go back to where we started, okay, so you're going to look up the mass of sodium, hydrogen, carbon, 3 oxygen atoms, add them all together, then take the mass of sodium and divide it by the total amount. So that first percentage on number 3 for the sodium should be in the high 20s, okay? Because if that number is right, I got to figure the rest of them are going to be right. And on that manganese dichromate, on that second one, that manganese should be around 15%. Okay? Cool with that. Okay. Now, on the mole conversions on number 4, I want to make sure everybody knows exactly how I want these done. So you got 0.238 moles of strontium hydroxide. So let's make sure everybody's cool. Because if the formula for strontium hydroxide is wrong, everything else is going to be wrong. So what's the formula for strontium hydroxide?
SR and then parentheses OH parentheses 2?
It is. Okay, why?
Because strontium has an oxidation number of +2, and then or hydroxide is a polyatomic ion. That's a negative one.
That's a beautiful answer.
Thanks.
Spot on. Absolutely perfect. Because here's what everybody does wrong. They write strontium hydroxide as SROH. Okay? That's what they do wrong. Strontium hydroxide, SROH. You have to pay attention to the oxidation states. Now, how could you look at the periodic table and figure out that strontium has a charge of 2+?
It's in the second column.
Yeah, it's in the second column. Okay, everything in the first column has an oxidation state of 1+. Everything in the second state has a charge of 2+, because it wants to lose those 2 electrons to be like the noble gas in the previous row going across. Okay, so your answer to that one with the grams. So here's what I want to see. You're going to take 0.238 moles strontium hydroxide. You're going to put 1 mole down here. And then you're going to put that molar mass of 121.62 grams. Now, here's the deal. At this level of science, you have to get out of your mindset that, well, I'm just going to get an answer. Okay, this class is going to be a train wreck. I'm more concerned about the process than I am about the answer itself. Okay, so if you just randomly write down numbers and I don't know what they mean, there's no point. Okay, this is going to be about a process. We're going to work through horribly complex problems. And the sooner you embrace this idea that, oh, I need to show working up the process, the better off you're going to be, okay? Because, excuse me, unfortunately, I've got to fight 12 years of your education where you just had to worry about the answer, okay? Hey, I got the answer, who cares? No. In this level, this is about showing your work. This is about showing the process. It isn't just about getting an answer that you're going to write down on a piece of paper, okay? This is the level of work that I'm going to expect. So, when you're doing relative atomic mass, at least go out to the 10th place, okay? At a minimum, go out to the 10th place. If you want to go out to the hundreds, that's fine. Now, you don't have to go out to like the hundreds, thousands place, okay? But at a minimum, go out to the 10th place. So especially when you get into like chlorine. So chlorine is 35.5, okay? So don't round that to 36. Don't round that down to 35. So at a minimum, when you're looking at relative atomic mass values, at a minimum, go out to the 10th place, okay? At a minimum, okay? If you want to go to the hundreds, that's fine. But don't go out past that. That's beyond what we need to do. If you feel comfortable stopping at the tenths, hey, stop at the tenths. Mr. Burkamp, I like writing down digits. Well, I'm happy for you. You can go out to the hundredth place if you want to. Okay? You don't have to, but a minimum go out to the tenths place. So that second one on number 4, you have that cobalt chloride. That number of moles should be around 0.2. Okay? It's an ish, but it would be something around 0.2. So again, show me that conversion, start with the mass, go from there. All right. So this is what we talked about on those net ionics. So does anybody have any questions on the front page? Everybody cool on the front page? Page 1, going once, going twice, sold? Okay, page 1 is done. So let's talk about page 2. So this is what I showed you yesterday. So we kind of rushed through that. We'll spend a little bit more time on it. So here is some magnesium nitrate, and it's a clear solution, okay? So is magnesium nitrate soluble in water?
Yes,
Yes, why?
because it's a nitrate.
All nitrates are soluble, there's no exceptions, all nitrates are soluble. So what that means is that it's like a tug of war. So if you go into the lab and you grab a bottle of potassium nitrate, it's a white crystalline substance, okay? And it's held together like in a lattice between these magnesium ions and these nitrate ions. So Okay, so as a solid, these particles are bound together, okay, the magnesium to the nitrate. So what happens is that when you put them in water, it's a tug of war on an atomic level. So typically, sometimes you'll see water drawn as like what I call the Mickey Mouse structure, okay? Looks something like this, where this is the oxygen atom, and these are the two hydrogens. So when you see this type of structure, they're not talking about Mickey Mouse, okay? It's a water molecule. And this is representative of like the electron clouds. So, and we'll spend a lot of time talking about water and why it has its unique properties. But basically, what we talked about yesterday, the water has a negative end where that oxygen is because it has more electrons in that end of it. And the hydrogen end is positively charged. So you have a negatively charged end and you have a positively charged end. That's what makes water such a good solvent. That's why it dissolves stuff. Okay? So basically, this is a tug of war. When these magnesium nitrate crystals hit the water, they're conflicted. Because the magnesium and the nitrate are going, man, we've been together, so we've been sitting in that jar in the chemical storeroom for a long time, man. We're tight, okay? You know, we've spent years together inside this jar. Tight, okay? And then there comes along this water molecule. The water molecule says, no, stop. Okay, look at me. I got a negative end and I got a positive end. I got something for both of you all. What do you say? Let's hook up, okay? And the magnesium nitrate's going, oh man, we've been together a long time. The water molecule's going, come on, let's party, okay? So the magnesium nitrate has to make a decision. Do I stay with who took me to the dance, or do I go hang out with the water molecules? So the nitrates, okay, they have a questionable moral background because they will leave anything to go with that water molecule. They're like, we're out of here, see ya, okay? There is no chance those nitrate molecules are going to stick around. They are of questionable moral content in the atomic world, okay? They really are. So the nitrates are going, we're out of here. We're going to go hang out with the positive end of that water molecule. And the magnesium's sitting there going, well, what do I do? I got this positive charge. Well, and the oxygen end of the water molecule is going, hey, I'm negatively charged, but hey, we can hook up because we're, you know, I'm negative, you're positive. What do you say? The magnesium goes, well, the nitrate already left me. What the heck? I guess I'll bond with you. So what happens on an atomic level, the hydrogen end of the water molecule is going to attract those nitrates. The oxygen end is going to attract those magnesiums. Now, you put your hand in water. Is your hand soluble in water? No, thank God, okay? Thank God it's not that, because if your hand was soluble in water, it would dissolve. It was like, oh, wash my hands, okay? Okay, this is bad. Your hair isn't soluble in water. It's like, you wash your hair? No, it's going to dissolve, for God's sakes, no, okay? So, but salt is soluble in water, for example. Okay, so you want things, we want certain substances to be soluble in water, we want other ones to be insoluble in water, okay? Limestone, for example, which is calcium carbonate. Limestone is insoluble in water. That's why we use it to build buildings. If calcium carbonate was soluble in water, guess what? We wouldn't build buildings out of it because what would happen when it would rain? Yeah, it would just dissolve. It was like, oh, my bad. Sorry about that house. It dissolved. I didn't understand my solubility rules inside. Blame Mr. Burkamp. This is all his fault. So that's cool that we have some. No, nod your head. Yes. Sand. What about sand? Soluble or insoluble?
Well, it depends on what it's made out of.
For the most part, sand is going to be insoluble, right? Because if sand was soluble, guess what? We wouldn't have sandy beaches. Okay? Because if sand was soluble, the first wave that came in, it's like, what happened to the sand? I don't know where it's going. Well, so much for that idea. This is bad. Okay? So sand, for the most part, is insoluble, right? So in this magnesium nitrate solution, okay, visualize this. The magnesium ions are existing, and listen to me, as magnesium ions, okay? If it existed as magnesium itself, it would look like this, and it would be a silver chunk, okay? So, by virtue of the fact that I don't see silver chunks in here, I got to figure that these are magnesium ions. If they were elemental magnesium, I'd see chunks of silver, okay? And so that's going to be important later on when we get into redox reactions. If you have the elemental form of a metal, it's going to be chunky. If you have the ionic form, it's going to be a solution, okay? So within here, we can't see it, but if we could like shrink ourselves down, we would see a Mickey Mouse shaped water molecule, and the nitrate's attracted to the positive end, and the magnesium ions attracted to the positive end, okay? Got that? It's a tug of war. Magnesium nitrate says, see ya, I'm out. Now, to this, we're going to add sodium hydroxide. Sodium hydroxide, soluble or insoluble?
Soluble.
Soluble. Why?
Because sodium is in the first column.
Yeah, group 1. Okay, alkali metals are soluble, right? Hydroxides are actually insoluble because it's bound up with the sodium. There you go. So the same thing's going to happen. When I mix up sodium hydroxide, it's a white powder. Which sounds like a drug deal, because a lot of like powders in chemistry are white powders. It's like, oh, I'm doing chemistry. Really? Whatever. Okay, so you're going to have this white powder of sodium hydroxide. You're going to put it in water. It's going to dissolve. Because again, the sodium says, woo! Ah, there's that negatively charged oxygen atom. I'm going to hang out with it. The hydroxide says, well, I've got a negative charge. I guess I'll hang out with the hydrogen end of this thing. So those bonds are stronger. So on an atomic level, here's one that has the nitrates, and then you have the magnesiums. And then in the other bottle, you have the hydroxides and the sodiums, okay? So now, we're going to mix these together. As soon as I do that, you'll notice, like yesterday, laws of chemistry so exist that we get this white chunk. Because if this didn't happen, it's like, oh, yesterday they worked, today they didn't. This is bad. Better go check my news feed, see if laws of chemistry are still, working. So out of this, I get this chunky precipitate. So basically what happened is this. When I mix these together, the magnesium said, ooh, there's some hydroxide ions. The nitrate said, ooh, there's some sodium ions. So these are going to be attracted to each other. Why?
Because of the charging.
Yes, they have oppositely charged, right? So basically what happens is this. The magnesium and the hydroxide go, whoa, sup, okay? This is like, Tinder on an atomic level, okay? They're going to swipe left or right, whichever direction it is. So the magnesium and the hydroxide are going to go, we have found love, true love. And so they're going to go, wow, this is cool. So what's going to happen is that the bond between these two is stronger than the bond with water molecules. So they go, oh, so good, right? So the magnesium and the hydroxide are going to hook up because that bond is stronger than it is to the water molecules. The water molecule is going to feel a little jilted at this point. The water molecule is going, really? Really? So this is how this is going to go. You see somebody else and you're out of your magnesium goes, yep, bye. Okay? Now, the nitrate and the sodium, they're attracted to each other because they're oppositely charged. But they're going, yeah, we're good. Okay? We're going to stick with water molecules. So the nitrate sticks with the water molecule, the sodium sticks with the water molecule. So that's why those remain still as soluble ions. The magnesium and the hydroxide, they're going soft. Okay? So, love me tender, you get a precipitate of magnesium hydroxide. So on the net ionic equation, you're going to have magnesium ions and 2 hydroxide ions forming MgOH2. Because the net ionic is going to show you just the things that have changed. So You got magnesium ions, you got hydroxide ions. The reason that this forms a precipitate is that this fundamentally changes the nature of how these ions exist. This existed attached to a water molecule. This existed attached to a water molecule. This changes because now these are bound together. The nitrates and the sodiums, they're still hooked up with water molecules and never change. So this is why those are called spectator ions. So it's like imagine again you're at a club, right? And you have this dance floor. And the sodium and the nitrate are watching the magnesium and the hydroxide hook up, and they're just chilling out going, sup, you guys knocked yourselves out. Okay? We're going to stick with the water molecules. And the magnesium and the hydroxide are going, whoa, sup? This forms a very strong bond, and it's going to form a precipitate. Got the idea? So on that first one, where you have the sodium hydroxide and iron 3 nitrate, okay? So your net ionic equation should look like this. You should have Fe3 plus 3 hydroxides yielding FeOH3. So that should be that first net ionic equation on number 6. Okay? Cool with that. All right. So, on that second one, silver chloride should be your precipitate. And on that third one, cadmium cyanide should be your precipitate. Okay? And make sure on net ionic equations that you balance on two different things. You balance on number of particles, and you balance on overall charge. So, this precipitate has no charge, okay, because it's bound together. So, if I take 3 positive charges and add those to 3 negative charges, I get 0, which is the same charge as over here on this product over here. Okay, so I have 3, I got 1 iron, I got 1 iron, I got 3 hydroxide, I got 3 hydroxide. So I balance on number of particles, but I also balance in terms of charge. Okay? Cool with that. Grand. Good. Okay. So on number 7, you're going to use that stoic. So let me kind of give you some hints on some of those. Just like on 7A, that should be between 1 and 2 moles. On B, that should be like around 5 grams. On C, that should be around 1 gram. On that molarity, on number 8, quick refresher on molarity. And molarity problems aren't tough if you keep one thing in mind. That molarity is moles per liter. Okay? That's the whole key to this. It's moles per liter. If you keep that in mind, all problems are pretty simple. So, on number 8, here would be the situation. Okay? I go to Morgan and I say, hey Morgan, I want you to measure out 45.87 grams of nickel 2 nitrate. We're going to put that in 250 milliliters of water, and I want to know what the resulting molarity is going to be. Okay? So, on number 8, there's a couple of ways you can work number 8, depending upon your preference. So, at the end of the day, you got to take the 45.87 grams of nickel 2 nitrate and change that from grams into moles. Okay? So, if you're a step-by-step process kind of person, one option is that you do this calculation by itself. And you say, okay, how many moles of nickel 2 nitrate am I going to have? And you get that number by itself. Okay? And some people like a step-by-step approach to this. I don't care. But what you have to be careful of, if you're going to do this as a step-by-step process, keep a lot of digits and then round when you get to the end. Okay, so when you take that 45.87 and you divide by the molar mass of nickel nitrate, don't round that number too much. Okay, keep a lot of digits. So you're going to get some number of moles, and then you're going to divide that by 0.250 liters, and boom, there's your molarity. Okay, so if you like a step-by-step process, Find the moles by itself, take the moles, divide it by the liters, boom, you're off to the races. Now, if you're like, oh, but Mr. Burkamp, I like working it in one big equation. Okay, fine. Start with the 45.87 grams of nickel 2 nitrate, some number of grams, 1 mole, and then down here is just divide by that 0.250 liters. Okay? So again, here's the deal. The units will lead you to the promised land. Okay, that's the absolute truth. The units will lead you to the promised land. So if you look at what's going to happen, the grams are going to cancel out. You're left with moles divided by liters. Voila, you get molarity. So the advantage of this is that you don't have to like write down the moles as like a separate answer. You can just work it all in one step. You don't have to round it. It's just one thing. So I don't care which one you do, but just don't randomly write down numbers and, oh, Burkamp will know what I'm doing. No, Burkamp won't know what you're doing, okay? What you want to do is lay this out so that I can see exactly this process on this conversion. Anyway, so both your answers to B and C on number 8 should start with a 3. And your answer to D should be around less than 1 mole. Like quite a bit less than 1 mole. Okay? Any questions on page 2? Okay, we're going to stop that camera for a second. I know you all been sitting. Stand up. Okay, so there's very few things that I'm going to expect you to memorize. This is one of them. So somebody had that sheet of like common things, the like ions and things like that I gave you. So let me see. Okay. So on this sheet where you have strong acids, so there are 7 of those. These are the only things I will expect you to memorize is the names and formulas of the 7 strong acids. Okay? So a lot of them you're already going to know. Hydrochloric, nitric, that type of thing. Basically, if you look at the 7 strong acids, most of them are actually, if you go down the halogens list, other than fluorine, hydrochloric, hydrobromic, hydroiodic. Okay? So there's a lot of your strong acids just if you go just down the halogens list. The only one that isn't is fluorine. The reason that I'm going to expect you to know these is because once we get into some more intense calculations, you have to know if something is a strong acid or something is a weak acid. The vast majority of acids that exist are weak acids. There's actually very few strong acids. So it's like, that's why I'm going to expect you to know the strong acids and not memorize all the weak acids. So therefore, it's like if you know what the strong acids are, and if it's not one of those, then by default it has to be a weak acid. Because mathematically, in a lot of these calculations, they're handled completely differently. Okay? So the first quiz is probably going to be early next week. Okay? See how some things play out. But, so on the first quiz, I'm going to expect you to know any four of the strong acids. Where I'm going to expect you to be able to write down the name and the formula of 4 of them. Okay? So, pick 4. Eventually you're going to have to know all 7. But you can pick 4. I don't care which 4. I'm going to give you space. You can pick whichever 4 that you want. You can put down the name and the formula. Like nitric, sulfuric. I don't care which ones. Okay? But eventually I'm going to expect you to know and have memorized those 7 strong acids. Okay. Now, so this is going to be important in terms of how you handle question number 9. Hydrochloric acid is a strong acid. So let's start with this idea. So what's the difference between a strong acid and a weak acid in terms of ionization?
Strong acid can ionize medium.
What'd you say?
Strong
Yeah. Strong acid is basically completely ionized. So here's the deal. And again, this boils down to a tug of war with water. So here's your water, okay? Here's this negative end on the oxygen. Here's this positive end on the hydrogens, okay? So when you take hydrochloric acid, which is a hydrogen ion and a chloride ion, okay? So you have a cation and an anion. Again, here's the recurring theme. This is tug of war. The hydrochloric acid, when you put it in water, is conflicted. The hydrogen is attracted to the chlorine because they have oppositely charged. And it sounds cute. Oh, they're hydrochloric acid, right? It sounds cute. They're a couple, okay? But you put it in the presence of water, and again, it has a decision to make. What's the stronger bond? Is there a stronger bond between the chlorine and the oxygen, and the hydrogen and the oxygen, okay, because they're going to be oppositely charged? Or is the bond between the HCl stronger? Okay, that's on an atomic level, that's the decision to make. So anytime there's a strong acid, basically what's going to happen is this. This bond is very, 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 very weak. So as soon as you put it in the presence of water, it's like, we're out of here. See ya. Okay, let's stay in chat. Got to go hang out with the water molecules. So this hydrogen is going to be attracted to the oxygen in. The chlorine is going to be attracted to the oxygen. So this is why a lot of times when you're dealing with acids, and you're going to see this written a lot. So if you take a water molecule and it's attracted to a hydronium ion, okay, so the terminology, that's a hydronium ion. And if you think about it, all that is a proton. Because if you look at a hydrogen atom is a single proton with one electron orbiting around it. You take away the electron, what do you have left? Oh, it's a proton. So a hydronium ion is just basically nothing more than a proton. That's all it is. So basically what happens is this. When you take that water molecule, that proton is going to become attracted to it, and it's going to form H3O+. Okay? So these two are used interchangeably. A hydronium ion, H3O+, they mean the same thing. Okay? This is technically more correct, right? Because this is what actually happens, is that proton becomes attracted to a water molecule and you form H3O+. So what happens here, and this is the whole key to this problem on number 9, you have 0.015 molar HCl. Okay, that's what you're going to start with. So what's going to happen is this. That HCl, you're going to put that in the presence of water. And what's going to happen is that you're going to form H3O+ and a chloride ion. Okay? That's it. So what's going to happen is this. These bonds to those water molecules are very, 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 very strong. They're much stronger than the bonds that hold the hydrogen and the chlorine together. So one of the things, did you all do rice charts? Have you ever heard of rice charts? Kinda? Okay, so what happened, we're going to live and die by rice charts. We are going to live and die by rice charts. So the R stands for the reaction. Your I column stands for the initial set of conditions. The C is going to be the change. And then the E line is going to be at equilibrium. So these all work the same way, and we are going to live and die by rice charts. Okay? So the sooner you embrace them, the better off you're going to be. Okay? Just get used to these. So here's the reaction and how we're going to work this problem. Here's what's going to take place. We're going to take HCl, we're going to put it in the presence of water, we're going to form hydronium ions and chloride ions. Okay? That's the deal. So initially, this is going to start off at 0.015 molar. I never worry about the concentration of water, so there's nothing there. Don't worry about that. And we're going to assume that everything over here starts at 0. So in other words, we're going to introduce this. There's no hydronium ions, and there's no chloride ions. So because it's a strong acid, and this is why you have to know your strong acids, because this is a strong acid, all of this is going to go away. You will not have any of this left over. Okay, this is all going to go away. So I'm going to go, oh, minus 0.015. It's all going to go away. And that gets added over here. Now, the reason that these numbers are the same, we're going to stop this for just a second. We're going to talk about cheese sandwiches. Okay? You know, what do cheese sandwiches have to do with chemistry? Come on, Berkey. Seriously. So pretend that this reaction doesn't exist. We'll get back to it. Okay, but we're going to take a small break and talk about cheese sandwiches. So in cheese sandwiches, I like my cheese sandwiches to be pretty simple. So it's one slice of bread, a slice of cheese, and then another slice of bread. So it's 2 slices of bread to 1 slice of cheese. Now, if I ionize my cheese sandwich, that's going to separate into 2 slices of bread and 1 slice of cheese. Okay? So it gets separated. That's what it's going to end up at, right? So imagine in a bag, I have 5 sandwiches. 5 sandwiches. I put them in the bag, shake them up, right? Out of these 5 sandwiches, how many slices of bread are going to end up in the bag? 10. So if I have 5 of these, I'm going to have 10 slices of bread, and I'm going to have 5 slices of cheese, right? Because I get 2 slices of bread for every 1 sandwich. So what's going to happen here is that I have 5 slices of bread, or 5 sandwiches, no bread, no cheese. I'm going to ionize all 5 of these. So I'm going to go minus 5, but then over here I'm going to put plus 10, plus 5. So once I reach equilibrium, I'm going to have 10 slices of bread, 5 slices of cheese. Okay? So, because there's a 2 here, the concentration of my bread is twice what I start with. There's a 1 in front of the cheese, so that just means that's the same. Okay? So you got my cheese analogy. Okay. Now, we're going to go back up here. Everything here is in a 1-to-1 ratio. Okay? So if this starts at 0.015, 0 and 0, I lose all of this, so this is why these numbers over here are the same. Because instead of like having 1 slice of cheese and 2 slices of bread, I don't like bread that much. So this is just a 1 slice of bread and 1 slice of cheese. So if I have 5 sandwiches, I get 5 slices of bread, I got 5 slices of cheese. Okay? So if it's a 1-to-1 ratio, this is a huge if. This is a huge if. If it's a 1-to-1 ratio, all of this goes away, it all ends up over here. So at equilibrium, I got no HCl left over. I have a concentration of 0.015 on my hydroniums and 0.015 on my chloride ions. Okay? That's what we've got. Now, let's talk about what pH means. So now we need to have a quick discussion about pH. So when you see pH, and we're also going to talk about pOH, we're going to talk about pKa, we're going to talk about a whole bunch of things that start with a P in front of it. What that P stands for is negative log, okay? Log base 10. Okay, it isn't the positive log, it's a negative log. So anytime you see P, you're taking the negative log of whatever comes after it. So when you see pH, that stands for the negative log of your hydronium ion concentration. Your pOH is the negative log of your hydroxide concentration. We'll talk about Ka later, okay? And actually, once we get into weak acids, we'll talk about Ka values. So, if you're talking, when you see a P in front of anything, it stands for negative log. So, when you look at this first question on the pH of a 0.015 molar solution of hydrochloric acid. So, you're going to take the negative log, because that's what P stands for, of 0.015. Okay, that's all you have to do. That's what that P stands for. So if you look on your equation sheet, so if you look on that equation sheet, right here, kind of on this side where it's got the AP chemistry equations and constants. So what we're going to deal with first, this whole unit is going to be based upon this whole system on equilibrium right here. So right here, you've got pH equals negative log of your hydronium ion concentration. pOH, negative log of your hydroxide ion concentration. Now, eventually we'll see why pH plus pOH add up to 14, but we'll deal with that later. So, here's the deal. And the only reason that we can take the negative log of 0.015 is because hydrochloric acid is a strong acid. If it was a weak acid, we couldn't do that because it would ionize completely. But because hydrochloric acid is a strong acid, it all ionizes, it all goes away, nothing exists as HCl. It all exists bound up with the water molecules. Got that idea? Okay? All right. Now, when you get to the pH of 4.57, what's the hydronium ion concentration? So with this one, basically, you're going to undo this. These are log base 10 systems. So basically, on that second one, you've got a pH of 4.57. So how do you undo a negative log base 10?
10 times the negative of the...
Not 10 times,
Or
but...
10 to the power of negative pH.
Yes. So if you want to find the, for example, on this one, what's the hydronium ion concentration? So you're going to take 10 to the negative 4.57. Take 10 to the negative 4.57, that's going to get you the concentration of your hydronium ion. Now here's how you can check that you got this right. When you get that answer, which should be something times 10 to the negative fifth, here's how you can check that your answer is right. Take that answer, take the negative log of that value, see if you get 4.57. If you do, you did it right. If you don't, you did it wrong. Okay? But that's where you have to understand what that P stands for. That P stands for negative log and not log. Okay? Cool with this. So your answer on that one should be something times 10 to the negative fifth. Now, when you get to that third one, you have hydroxide ion concentration of 2.74 times 10 to the negative fifth. So one of the things when you deal with pH, and this will make sense later on once we get into labs, when you write down pH values, you always have 2 digits to the right of the decimal place. Okay? Always, even if there are zeros. So when you write down a pH value, you want 2 numbers to the right of the decimal place. Like if, let's say you get 4, you write that as 4.00. If it's 4.1, you write that as 4.10. So any pH, 2 decimal places to the right. Count them. Dose. 2 places to the right, even if there are zeros. So what's happening on this one is that once we want the concentration of the hydronium ions. So if you look down below, on that green sheet, you have Kw equals hydronium times your hydroxide equals 1.0 times 10 to the negative 14th. So, what this number represents is called the auto-ionization constant for water. Do not tell me, amongst the list of things that annoy me, okay, like for example the word decelerate, air molecules, for the love of God, don't ever say air molecules. There's no such thing as an air molecule. What's happening here is that what we're saying is that if you multiply the hydronium ion concentration times the hydroxide ion concentration, you always get the same number of 1.0 times 10 to the negative 14th. Okay? That's what this auto-ionization constant of water. This is not water. Don't tell me, oh, water is 1 times 10 to the negative 14th. No, stop. Okay? That is not water. Okay? It's auto-ionization constant of water. So what that means is that these two numbers multiplied together always equal 1.0 times 10 to the negative 14th. So this is why when you have neutral water, okay, these two concentrations are the same. Well, the only way that happens is if this is 1.0 times 10 to the negative 7, and that's 1.0 times 10 to the negative 7, and then you multiply them together, you get 1.0 times 10 to the negative 14th. Okay? So the reason that we deal with hydronium ions is a measuring process. So when you deal with pH probes, you do a lot of measurements with pH probes. pH probes are designed to measure one thing. They measure the hydronium ion concentration. We don't measure chloride ion concentrations. We don't measure hydroxide ion concentrations. It's a one-trick pony. pH probes measure one thing, and one thing only. That's the concentration of hydronium ions. But if you know the concentration of hydronium ions, then you can use that to figure out, like for example, the concentration of the hydroxide ions. So I will never, don't ask them, like, hey, Mr. Burkamp, can I have the POH probes? No, you can't, okay? No, they don't exist. We only have pH probes, because that's a one-trick pony, but it's a good trick, okay? So, you're going to find the hydronium ion concentration, so you can take 1.0 times 10 to the negative 14. And a word of caution, make sure that when you're doing this in your calculator, hit that EE key to the negative 14th. Don't type in times 10, because it'll screw up your order of operations sometimes if you don't hit it right with just like the brackets and everything. So instead of punching in times 10, type in 1.0, hit that EE key, and then type in negative 14. Divide that by that hydroxide ion concentration. Boom, there's your hydronium ion concentration. So on that one with the hydroxide ion concentration, if all goes well, your pH should be around between 9 and 10. Okay? So that's going to be somewhere between 9 and 10. Now, when you get to that pH and POH, you're going to dissolve lithium hydroxide in 600 milliliters of water. So the first thing that you've got to do is convert the grams of lithium hydroxide into moles of lithium hydroxide, and then divide that by the volume to get the molarity of the lithium hydroxide. So again, what's happening is that the lithium hydroxide is ionizing at a 1-to-1 ratio of lithium ions and hydroxide ions. So if you know the concentration of your lithium hydroxide, you automatically know the concentration of the hydroxide ions. Then from there you can find the pH and the POH. So on that last question with that pH and the POH, your pH should be a little bit less than 14, and your POH should be a pretty small number. Because, and this is also on that sheet, your pH and your POH add up to 14. So if you ever know your pH, you subtract that from 14, there's your POH. Okay? On the question about the grams of lithium hydroxide required to neutralize the nitric acid, start with the reaction of nitric acid and lithium hydroxide. It's a double displacement reaction. You get lithium nitrate and water. Why do we always get water when we combine hydrogen and oxygen? Mother Nature is a prima donna. What do you think the most stable and lowest energy existence of hydrogen and oxygen is? Water. If hydrogen peroxide was the most stable form, our oceans would be filled with hydrogen peroxide. Rain would be hydrogen peroxide, okay, which would be really weird. If you ever seen hydrogen peroxide, if you ever had like a cut that gets infected, you put hydrogen peroxide on it, it like bubbles up. Okay, so it's like, oh man, I got an infection, I'll go stand out in the rain. Okay, that'll clean it right up. Okay, if you ever want to drink it, because it would be bad for you, but yeah. So if hydrogen peroxide was the most stable form, we wouldn't be here having this discussion, but thank God water is the most stable form of it. So, anyway, so on that question with lithium hydroxide and the nitric acid, that should be around 1 gram. And that next one with the strontium hydroxide and the nitric acid, that should be between 2 and 3 grams. Okay. On number 10, without electron configurations and electron dot notations, remember on the electron dot notation, you're only showing the dots that are in the highest occupied energy level. Okay, you don't want to see all of them. At most, when you do electron dot notation, you should have at most 8 dots. You're never going to have like 10, 12, anything like that. You're only going to have 8 dots. Most, okay? At most, you can have 8 dots. On that last one, how many single unpaired valence electrons are in the following atoms? At least one of those answers should be 0. Okay? At least one of your answers should be 0. When you get to question number 11 about the redox reactions, so let's make sure we're starting off right with that. So basically what's going to happen is this. It's going to be the similar type thing. So I'm going to take some hydrochloric acid, like so. I'm going to use magnesium, but it's the same reaction. Okay? And I'm going to drop in piece of magnesium, right? And right away it starts to bubble, okay? So anytime you have a single displacement reaction, it's always a redox reaction because, like for example, I'm taking the elemental magnesium and I'm changing it into a magnesium ion. The same thing is going to happen with the zinc. So remember, when you have the elemental form of anything, that has an oxidation state of 0. So, let's see. Okay, so what is reduced on number 11 is the hydrogen, okay, because if that's wrong, everything's going to be wrong. And your reducing agent and your oxidizing agent, remember your reducing agent contains what is oxidized, and your oxidizing agent contains what is reduced. Yes?
On the reducing and oxidizing agents, we put the whole, like...
Yes, you put the whole smash.
Okay.
Yes. Yes. So like one of your answers should be hydrochloric acid on the reducing agent or the oxidizing agent.
But for the oxidized and reduced, you only
That's
put
the
ion.
individual element.
So it's like the ion.
Yeah.
Right?
It's just, that's the individual element. Yes?
You know when we've been out?
At 1:15.
Okay.
Okay. So, Morgan, come up here for a second. I don't know if we have enough. So the other thing, so I collect this hydrogen gas, so hold this test tube. So we'll make a little fire.
Do you want me to move the camera to it?
That's okay. So hand me that one. So, didn't collect enough. If we had collected enough, you ever heard the test tube bark? Where you put the flaming cylinder in there? I didn't collect enough hydrogen that should have popped. Anyway, we'll do that again tomorrow. It's like, well, that was anti-conforming. Okay. So, in the name of time, when you get to this question about the Ka of acetic acid, and so here's the deal. So the Ka of acetic acid is 1.8 times 10 to the negative fifth. What's the pH? Now, here's the deal. Assuming that you all have a basic idea of Ka. So if you look on this sheet on how Ka values are calculated, Ka is the hydronium ions times your anion concentration divided by Ha. Now, here's the significance of K. Anytime you see an uppercase K, the only time, listen to me, the only time you see K is when it's at equilibrium. Okay? So, no matter what it is, KSP, KA, KB, doesn't make any difference. K is only used at equilibrium. So basically what's happening with this acetic acid is that these numbers multiplied together, Mother Nature wants that to equal 1.8 times 10 to the negative fifth. Okay? You guys have to go. Okay. We'll finish this up tomorrow because I want to spend some time going over this weak acid concept. So just we'll hand this in tomorrow. We'll take this up. We'll work number 12 and 13 in class tomorrow. So if you guys need to go. We'll call it a day. All right, Morgan.